Okay, so we are now in section 13.7, and we're going to look at a theorem called Stokes' theorem. Now, Stokes' theorem, you remember Green's theorem. So Green's theorem in section 13.4 was a theorem that would allow you to compute the work that a force field does in moving a particle once around a closed path in two-dimensional space in the XY plane. And the vector field was a two-dimensional vector field. And one nice thing about the Green's theorem is it worked for like all vector fields. In other words, the vector field could be a conservative vector field or a non-conservative vector field. Of course, if the vector field was conservative, then with Green's theorem, the work that a force field does in moving a particle once around a closed path in a conservative vector field, that work just equals 0. But if you have a non-conservative vector field, Green's theorem is extremely helpful. But the thing is, we're restricting ourselves with Green's theorem to vector fields in two-dimensional space in the XY plane. Well, what if you had a vector field? What if you had a closed curve, a closed path, C, in three-dimensional space? And you wanted to find the work that the vector field does in moving the particle once around that closed path. Well, to do that, you have to use a theorem called Stokes' theorem. And that's what section 13.7 covers. So it says here, Stokes' theorem can be regarded as a higher dimensional version of Green's theorem. And again, where Green's theorem relates a double integral over a plane region D to a line integral around its plane boundary curve, Stokes' theorem relates a surface integral over surface S to a line integral around the boundary curve of S. So let's just, get right to the picture here. So here's figure 1, and you have a closed curve in a three-dimensional space, and it's surrounding a surface. So in other words, that surface S in figure 1, the boundary of the surface is that closed curve C. You see that in figure 1? The boundary of the surface, okay, the rim or boundary of the surface, like is the closed curve C. So think of a balloon. A balloon, you blow up you just think of blowing up a balloon a little bit. The balloon is the surface, right? And the boundary on that surface is where the circle where you blow the balloon up, the edge, I guess. I don't know what you call that actually, where you blow the balloon up. It's the lip of the balloon, I guess. But you know what I'm talking about. It's the same kind of situation here. And you see in figure 1, okay, well, of course, we always have to talk about positive orientation. So positive orientation are the normal vectors going upward from the surface. And if you picture a person walking along that curve, the surface is always on his or her left. Okay, so the surface, if you picture like you have a man there walking along that curve C, which is the edge of the surface, as the man walks along the curve C, the surface is always on his left. Okay, and his head is pointing in the direction, by the way, of the normal vector. All right, so this is called positive orientation. And we are interested in the work that a vector field does in moving a particle once around that closed path. Okay, and the Stokes theorem gives us a way to find that work. Okay, so let me take off this here. This is Stokes' theorem right here. The work can be expressed as a flux integral. As a flux integral, you see that d sub s, the s is in bold. That means you have a flux integral where the vector field is the curl of your vector field. An absolutely amazing, amazing theorem. Amazing theorem. And I think it's worth mentioning a little bit about Stokes here. Usually there's a biographical note here. Sometimes it's a little hard to find in the ebook, but let me see here if I can find it. I can't find it, but I'll just mention here. So Stokes' theorem was named after the Irish mathematical physicist Sir George Stokes. He lived from 1819 to 1903. He lived to be 84 years old. That was pretty good back there. He was a professor at Cambridge University and was especially noted for studies of fluid flow and light. What we call Stokes' theorem was actually discovered by the physicist Sir William Thomson, known as Lord Kelvin. How many have heard of Lord Kelvin? He lived from 1824 to 1907. Very famous physicist. Charles has heard of him. Okay. And Stokes learned of this theorem in a letter from Thomson in 1850 and actually asked his students to prove that theorem on an examination at Cambridge University in 1854. So that was, the exam, prove this theorem. But they don't know if any of the students were able to do so. It was so long ago. But they go through a proof in the book. It's quite involved, but you're welcome to look at it. They do a proof of a special case of Stokes' theorem. But let's go ahead here and, go down a little bit further. Okay, so I just want to go down a little bit here. Yeah, I'll just mention this. It's worth mentioning. So in the special case where the surface is flat and lies in the xy plane with upward orientation, the unit normal vector is the k vector, and the surface integral becomes this double integral. But again, generally, there are special cases for certain surfaces where Stokes' theorem can be expressed in other ways. But my philosophy is, I don't like worrying about other formulas. I like to use one formula, and there's the Stokes' theorem formula. So let's go ahead and look at an example here. Let me bring up an example here from section 12.7. Okay, now this example is actually from your book. It's example 1 in the book, but I'm going to work through it with you. Okay, so let me give you a moment to copy this example down. Okay, so let's take a look at this problem. So first of all, the notation here where you have the integral with the circle on it, that means the circle means you have a positively oriented curve. Positively oriented curve. And positively oriented curve means that the normal vectors point upward from the surface. Okay, in other words, there's a surface S bounded by the curve. We're assuming then that the normal vectors to the surface are pointing outward. Okay, so positive orientation, outward from upward and out from the surface. Okay, outward. So we have this vector field. Okay, and the vector field is acting on a particle moving along this closed curve C. The closed curve C is the curve of intersection of this plane and this cylinder. Okay, so naturally, if a plane intersects a cylinder, it intersects it at an oblique, at a curve, like an oblique ellipse. Okay, so the particle moves around that ellipse where that cut is, and the surface S surrounded by that ellipse is, we're assuming that the particle is moving in such the direction such that the surface S is on the left as you walk around. I'll show you here. So let's go, you know what we need? We need a picture, right? Let's get a picture. So this is what I'm talking about. Here's a picture. Here's a picture of the situation. The plane cuts the cylinder, and you know, let me just circle this again in blue. The plane cuts the cylinder and creates a closed curve right here. The closed curve is an elliptical curve, and we are assuming the particle moves around the curve in the direction of the arrow. And if you notice, if you were to walk along that curve in the direction that the arrow shows, the surface S inside the curve would always be on your left. Okay, so we want to find the work that the vector field does in moving the particle along that curve. Now, since I'm computing a flux integral, remember, what is Green's theorem? Okay, Green's theorem says that this work is equivalent to the flux integral where the vector is the curl of your vector field. Now again, this is not always true, right? This theorem is for the special case where you have a closed curve, and you're working in three-dimensional space. So theorems like Stokes' theorem and Green's theorem are not always applicable, right? It depends on the situation. And that's one of the things for your final exam that you're going to have to recognize, right? Given a situation, do you know what theorem to apply? Okay. Now, you can't apply Green's theorem to this situation because your curve C here in red, your curve C is in three-dimensional space. Okay, Green's theorem is when the curve is in two-dimensional space in the xy plane. So since I have to compute a flux integral for Stokes' theorem, okay, for, you know, Stokes' theorem, since I have to compute this flux integral here, I better get the parameterization for my surface. Well, my surface S is again, it's enclosed. It's enclosed here inside the inside that curve. And what is that? Well, is the surface S part of the cylinder or part of the plane? Is the surface S in the picture there part of the cylinder or part of the plane? It's part of the plane. That's right. And there, that's good, Ellie. That's good, Charles. Therefore, the parameterization is for the plane, but not the whole plane, right? So how would we parameterize the plane? Well, y plus z equals 2, so z equals 2 minus y. Has to, it has no choice, right? Then x and y are your free parameters, but along for any point here in this surface, x squared plus y squared would be less than or equal to 1. So we have our vector equation for our plane, and we have our restrictions on our parameters. So, okay. All right, well, all right. So now I'm going to find a flux integral. So I know how to find a flux integral. I have to get the derivatives of my vector function, my vector equation, r sub x, r sub y, and take the cross product. If I do r sub x cross r sub y, it ensures that there's outward orientation on my surface. Okay. Why is that? Well, when I do the cross product, I get the vector j plus k, and that points outward from my surface S. So you always have to check this, class. You always have to check when you do your cross product that the vector you get is pointing outward in it's pointing outward. If assuming you want positive orientation. Okay, and clearly j plus k would be like a vector. Got to be a little careful here. Hold on one moment. Yeah, absolutely. J plus k would be like maybe I'll put it in blue. Hold on. Got to use my little. Here's the vector. That vector is j plus k. Doesn't move at all to the front or backward, but it goes, to the right 1 unit and up 1 unit, j plus k. So the orientation's right. Okay, what's the next step? Now that I have now that I have this cross product vector, what about the vector field? What do I need to compute for the vector field? Well, what's involved in Stokes' theorem? What's involved in that theorem? The curl. That's right, Ellie. So we're going to compute the curl. Okay, so I'll go to the next page if I may. Are there any questions on this part? Give me a thumbs up if you're ready to go to the next page, and we'll go to the next page. Okay, very good. Looks like everybody's ready to roll here. Good. Okay. Here we go. Here I'm computing. So my vector field F was negative y squared I plus xj plus c squared k. So hey, I got to compute the curl just like you do. So I put in the steps here, and I'm going to get the vertical vector 1 plus 2y times the k vector. Let me give you a moment to copy this down. Please let me know if you have any questions. Okay. Are we ready to move to the next page? Are there any questions? How many of you use this way of computing a curl? How many of you use this as opposed to like the regular definition? Okay, Charles does it that way. And Juliana, yeah, I just find this so much easier. Okay, well, if we're good, I guess we'll move on here. So now we, we're ready. We're ready to compute to apply the Stokes theorem. Okay, we're ready to apply it. Okay, and so by Stokes theorem, the work is equal to this flux integral. But we know how to compute a flux integral, right? This here. This here is the flux integral, but the vector is the curl of the vector field. Well, the curl of a vector field is itself as a vector field. Well, here then is the formula that I use for computing that flux, and now it's just a matter of putting in the curl. The curl of the vector field is 1 plus 2y times the k vector, and we're going to dot it with the j plus k vector. And I'm going to, well, the parameters x and y, the restriction was that x squared plus y squared is less than or equal to 1. That's a circle of radius 1. So I'm going to go ahead then and use some polar coordinates. And these are important things. So like now, remember, of course, for your work that you're going to be turning into me, for exam 3, I'm going to want to see your double integrals and triple integrals, right? I need to see that you can compute those, that you can work them out by hand, right? It's fine to use MATLAB to help you verify things, but for the work, I do need to see your work. Okay, so how many use MATLAB to help them verify double integrals that they worked out on exam 3? Was MATLAB helpful? Okay, excellent, Ellie. Excellent, Charles. Good, good. Okay, okay. We'll touch base on that, Charles. I see what you're saying. You catch mistakes. I see. I see. I got you. Now for this problem, actually, this double integral, I actually worked out. When you're ready, I'll go to the next page. And okay, Charles is good. Ellie's good. All right. Okay, great. Madeline, Gordon, Juliana, wonderful. All right, everybody looks good here. Well, here we go then. So I'm going to iterate. Well, let me just see here. Okay, so I'm going to naturally, iterate the integral. Okay, and there's no, you can't like write the double integral as a product of two single integrals for this. You're going to have to just, work it out. So the inner integral is with respect to r. Naturally, I'm going to distribute the r. So r times 1 and r times 2r times the sine of theta. And then I get r plus 2r squared sine theta. The antiderivative with respect to r would be r squared over 2 plus 2r cubed over 3 times sine of theta. The limits go from 0 to 1, your r. And I feed those limits in. And now becomes a calculus 1 problem or calculus 2 problem. And when you work it out, in the end, the work is going to be equal to pi. So this means overall that vector field, whatever it looks like, it helps that particle move along that closed path, C. And you're able to graph, vector fields, right? Absolutely amazing. Are there any questions on this example? Okay, now sometimes you can actually we used, well, sometimes you have a surface integral that if you want to compute it, you can actually utilize the Stokes theorem to help you as well. But that actually comes up in the second example in section 13.7, and I'm going to talk about that on Wednesday. But let me just see here if there are any questions here. Okay, if there are no questions, let me stop the recording.